Houston, we have a podcast.
Hi, Sue and Steve. Thank you so much for joining us here today on Houston, we have a podcast.
Nice to be here.
Great to be here today.
We've got a lot of exciting things to talk about. But before we dive into Intuitive Machines 2, the second mission coming up, a little recap of what IM1 was like, I want to know a little bit more about each of you. So, Sue, we'll start with you. Tell me about where you're from, what you studied in school, other roles that you've had up until this point.
I came from a place that felt very much like Houston the last 2 days, up in northern Wisconsin, and got my PhD in astronomy, astrophysics. From there, I went to Houston, here, in fact, to JSC to be a postdoc and started working on spacecraft missions, the Hayabusa mission that brought back a sample from the asteroid Itokawa. Since then, I then took a position as a physics professor in Southern California, then popped back to be a space scientist, because how can you pass up the opportunity to work for NASA full-time for the rest of your life? I think you can't pass that up. And have done things like building a telescope and studying comets, asteroids, orbital debris, and even helping to discover some exoplanets as well around some ultra-cool dwarf stars. And that is their actual description as well as their vernacular description, I think.
That's a really broad background. You've gotten to do a lot of different things.
Yeah, it's been a lot of fun. So even though my background is as a scientist, I like to play engineer on the side as well. And so that's really helped a lot in preparing for missions like this.
Steve, tell me, where are you from? How did you get into the space world?
Well, that's an interesting story. I'm from Pennsylvania, Philadelphia area, and my family was all blue-collar construction workers kind of thing, and I had this fascination with technical things and how things worked. So while everybody else was thinking about how to build things, I was thinking about how to build technical things. And so I wanted to be a pilot. I went to Embry-Riddle Aeronautical University in Daytona Beach. And I found out very quickly that I probably couldn't afford the degree to get a degree and then to learn flying lessons and all of that. So I went into aeronautical engineering, which is better anyway, because you get to learn how everything works. And while at Embry-Riddle, unfortunately, I was witness to the Challenger disaster as it flew and had the accident over Florida. And so I saw it as I walked across the campus. And I just had a feeling that someday I would be working in the space program. That was the moment that I recall. Well, I went back to Pennsylvania, worked on engineering, helicopter systems, mechanical systems, that kind of stuff for the Army helicopters. And then I ended up leaving there and getting a job at NASA at Kennedy Space Center, of all places. And I was in operations for a while and became a shuttle test director, where I directed launches of the space shuttle and landing and the convoy commanding of the return of the shuttles, and ended up leading the launch and landing division at NASA. Well, then we had the other accident, the Columbia accident. And I was in charge of putting all the 85,000 pieces of debris back together and, determining the forensics of the accident from the debris, and led a team of about 400 people there at the shuttle landing facility. Well, that was such a high visibility activity that people from Johnson Space Center noticed and asked me to move to Johnson Space Center, where I became the head of engineering for all of the human spaceflight programs for Johnson Space Center. And I led that for about 7 years before becoming the deputy director of Johnson Space Center. So I was steeped in engineering of human spaceflight. And after about 25 years at NASA, I didn't work my whole life at NASA, but a lot of it, I formed Intuitive Machines. And I am the co-founder, president, and CEO from its inception. And we started as a think tank, and we had 25 inventions in the first 5 years of the company, and 4 ventures that spun out into other companies. But we really didn't have a true idea of who we were. We were just solving tough problems using engineering, until the moon became of strategic interest again in 2018, where I guess there was a strategic directive from the National Space Council that said the moon is of strategic interest, which is Strategic Directive 1, which says we will spend money to put humans on the moon again. And somebody came into the office and said, you guys are the best lunar landing company there is. We weren't even in the lunar landing business at the time. But we had done that at NASA. We had built Morpheus, Project M, the liquid oxygen, liquid methane lander that we flew like 37 times. It was an Earth-based test bed. The project was originally to put a walking robot on the moon in 1,000 days, like speed, entrepreneurship, clear technology advances, one of those. And so inside of NASA is where I learned about entrepreneurship. And that's when I got the bug to start a business. And so when the moon became of interest, we pivoted the whole business to putting in a lunar infrastructure and building a lunar economy. And the Commercial Lunar Payload Service contract was how that dream was reignited. And here we are in 2025 now, working on our second mission to the moon.
So what year did you found Intuitive Machines?
We founded Intuitive Machines in 2013.
Okay.
And we've been in business, for 11 years now, going on 12.
Yeah.
And if you're going to want some sort of a problem that you really need engineering to solve, flying to the moon is a really excellent way to take that kind of background with all of your employees and apply it to a real world problem.
Yes. First commercial company to ever land on the moon successfully.
Oh, yeah. We're going to talk about it for sure. Sue, how did you get involved with Intuitive Machines, but on the NASA side?
So I had come from the Orbital Debris Program Office, and my goal there was to make sure that we had a telescope that was built on an island in the middle of nowhere, next to nothing, called Ascension Island, the MCAT telescope. And as that lead for the project, it was myself and one other woman that really led the design and build of the MCAT telescope. I learned a lot of project management, how to do engineering. If anybody's ever written requirements, you know that if it isn't difficult, it probably isn't written well. But all of those pieces are the different kinds of pieces that you need in order to understand how to develop payload projects. And when CLPS, we had finished building the telescopes, gotten it to the point of operational, the contractor side took over that side of the telescope. And the new challenge that CLPS offered was being able to take all of that background combined with my science background and be able to apply it to missions going to the moon. So even though my background in comets, asteroids, orbital debris, exoplanets wasn't specifically lunar, all of the challenges that you have to put together and all of the things you need to figure out how to do, the science and the engineering, dovetail really well into what we do as project scientists in helping to ensure that the payload teams are ready for operations and even understanding the engineering side of the integration onto the lander. So that's how I ended up going into CLPS. From there, the CLPS office had a number of task orders that had already been assigned to particular vendors. And they're the ones that decided who was going to be assigned to which task order. So it was somebody up at headquarters who made the decision on which task order I would be assigned to. Ironically, when I was selected for the Intuitive Machines task order, I turned to my husband, who happened to have led Morpheus back in the day, and thought, okay, well, this is going to be really excellent because when I have all the engineering questions about how Morpheus runs, we could just, hit pause on the TV on the couch on the weekend and have a little tutorial about how LOX methane engines work. And I can tell you that's happened on a number of occasions. Goodness. So it's worked really well. His background right now is working on the Gateway program, but all the Morpheus background has been really helpful for my learning curve in how landers work as well.
You have your own subject matter expert in your house.
Exactly.
Sue was quite upset with me when I gave John Lanson a tour of the mission control before she got an opportunity to tour mission control. So I remedied that, gave her a tour.
Yeah. So it was, we were in the middle of the mission and I had to sneak him on site because he was so excited. He knows so many of the people that work at IM, having worked with them at Morpheus. So I was waiting to sneak him in, looking around the corner, the elevator doors open, and out he walks with Steve and goes straight into mission control. I'm like, wait a minute. Oh. No, it's great. He definitely earned that offer from Steve.
Yeah, he sure did.
Wow. Well, let's talk about IM1. Intuitive Machines' first mission to the moon. Like you said earlier, you're the first commercial company to put a lander on the moon. I got to be there that day. It was really exciting at Intuitive Machines. Just a very small part of the broadcast, but oh my goodness, it was so electric. Everyone was so excited. It was buzzing and, figuring out last minute details as, we were preparing for descent and landing. So what kind of expertise did you rely on to make that successful?
Oh, wow. There's decades of experience, centuries of experience within the team at Intuitive Machines. And, I think there's a lot of secrets or tricks of the trade or, just hard work or organizational items, leadership items that you could quote to say, you could write a book about here's why we were successful. But the team was so mission driven, so focused on being successful. We didn't even prepare for failure. We were determined to make it work. And, a lot of hard work and long hours went into building the lander, learning how to do it. Because when you're flying to the moon, doing a first thing that's never been done before, you can't do it like everyone else. There's no textbook. So we're flying fixed price to the moon for about $100 million in a span it takes to get an undergraduate degree, about 4 years. And you had to throw the rule book out and figure out a way not to be held up by any obstacle, technical, regulatory, whatever reason. Contractually, you had to get to the moon somehow. And we put that into the team where they were solving problems all the time. Whatever came up, they would tackle that problem and find a way to get through it. So when we approached the mission, we had that in our culture already, where there was no problem that we couldn't find our way through. Now, as we launch the mission and we start to fly it, we're learning how to fly a mission. It's like you build a Ferrari never having learned to drive a car. And you're supposed to, right? So
That's true.
How do you drive a Ferrari? Well, how do you drive a Nova C lander? And we found that it took us some time to kind of sort out what was going wrong, what operationally we could fix. But Odie, our lander, his nickname, flew beautifully. And when we took the constraints off, we loosened up some of the error bands. We kind of let it fly more autonomously. It performed beautifully. And so we're very excited, but we have this saying where all the way through building the lander and up to flight and through flight, we were getting, bitten by alligators that any one of them could have taken the mission out. And our job was to turn the alligators into snapping turtles so that they sort of hurt you, but they weren't, deadly or mortal.
It was very interesting to watch it from our side of things. We started out with NASA being the customer and Intuitive Machines being the ones it was their mission, and we were just one piece of that mission. But as things progressed, and there were all of the different pieces that we needed to fit together, we really formed as a team and really started to just sit down at the table. We were having conversations in the hallways and in the back rooms and anywhere you could find somebody. We were really working together. It very much felt to me the whole time during the mission like living a movie, right? You watch Apollo 13 and all the challenges that they have to fix, and watching their team 4, which was the troubleshooting team, where they would come in and say there was this thing that they were working on. And the next thing you knew, okay, we solved that. Oh, but there's this other thing. And then they would solve that. And watching them go through that process of all the troubleshooting and just solving them one after another, it was really inspiring to see them working so hard and so passionately together as a team, including having bunks and,
cots in the office.
Cots in the office so that people could actually take a little rest, but still be available because they are so focused and so dedicated to the mission succeeding.
That's fascinating, and I'm glad that you touched on that because it makes me think about, we recently had Gene Kranz and Jerry Griffin, Fred Hayes on the podcast, and so these are men who were in all of those firsts, those Apollo firsts and even earlier. And so I'm thinking, how do you plan for a spacewalk when you've never done a spacewalk? And so hearing all of the expertise, like you said, Steve, it's really decades of experience that you have on your team into this. And I would be interested, Sue, in learning more about how do NASA and Intuitive Machines work together to make sure both parties' needs are met, and that's both during mission planning and execution.
There are a lot of pieces that go into that puzzle, right? We have people on our side who, for each task order, there's an integration manager. Frank Marino is our integration manager, and I'm the project scientist. And project with the J is we've identified ourselves as the PJs, which is great because so much of our planning is done from the confines of the home in our PJs. So I took that to heart. Yeah, slippers during the home mission just to make sure that we're represented. So in the process of planning, we have regular meetings, making sure that we have the plan set aside for how we integrate things properly. We have separate meetings set aside to make sure that we're talking with the payload teams and with Intuitive Machines on how the operations happen. There's plenty of this is how we're going to do it, as well as having sims, tabletop walkthroughs, things of this nature in preparation to make sure that we understand how to operate, they understand how we want to operate, so that once we're at the point of the mission phase, that's comfortable. So especially if things don't go exactly as planned, we have the process in place for how we're working with them really as a team.
It's quite a collaborative effort, I think, working with Sue and her team and NASA and Intuitive Machines working together. Badgeless, at some point. If you think about it, beyond just the CLPS program, we had Johnson Space Center helping with tanks and with analysis. We had actually embedded a crew of NASA mid-career people in the company to help us develop the Nova C. They had real tasks to do, and we had worked that with the center to exchange employees or workforce. We worked with Glenn Research Center on a technology to measure the quantities in the tanks while we're flying. So it's called RF mass quantity gauging. So that worked well. We worked with Langley Research Center on the NASA Doppler LiDAR, these lasers that we reprogrammed into the laser rangefinder registers when the rangefinders wouldn't work. We worked with Marshall Space Flight Center, Jet Propulsion Laboratory on the Deep Space Network, Kennedy Space Center, all of NASA, plus the FAA. Plus, globally, we worked with our 8 different ground stations in 6 different countries. It was quite an international, globally integrated effort, and primarily with Intuitive Machines and NASA together. It was great.
And let's not forget the other very important people, right? We talk about the technical, but the procurement side, getting the contracts in place, the PAO folks, both sides are working together. So we have our PAO folks and their PAO folks. So those are the people where they are on the down and in and may not get as much face time, but are super critical for the success of the mission as well.
Yeah, and to share the story like we're doing today.
Getting the story out, was amazing. Yeah, it's been fantastic.
So after touchdown on IM-1, the lander tipped over a little bit. It was really exciting waiting for the call that it had successfully landed. And then it took a couple of days, found out that it had tipped over a little bit, but you were still able to gather some of the data that you were looking for on that mission. So what did you learn?
Oh, essentially we gained and collected all the data that NASA had asked for. I think there was a few things that didn't quite go exactly right. But when we went to do the powered descent all the way down to the surface, we found out the rangefinders, the laser rangefinders or laser altimeters weren't working. We found that out and tried to figure out a way around it. But as a result, we landed at a vertical descent rate that was a couple meters per second faster than what we wanted. We wanted 1 meter per second. I think we landed at 3 meters per second. And then our horizontal velocity across the surface was about 2 meters per second. So we caught one of the landing gear and it broke. And therefore, when we went to stand up, it just gently leaned over and it was on a hill. So it was about 30-degree angle. But we learned how to communicate when your antenna is pointing right at the surface. So we bounced the signal out of one antenna off the surface, did reverse polarization into another antenna, and then back down to the ground. So we learned what multipath was on the south pole of the moon, which was a concern by the NASA folks on how are you going to operate on the moon at the south pole where you're at a low angle communicating back to Earth. And we did that because we were at a very low angle to the surface and we were communicating. Everything came back on that one little antenna, receiving the signal having been bounced off the surface back into the vehicle. So that was quite an interesting thing. But we learned a lot about the environment. We learned about the dust plume that was coming out from underneath this liquid oxygen, liquid methane engine. And as we approached the surface, you could see the dust and the ejecta, they call it, going straight out from the bottom of the lander, not in a plume cloud like you would think, but straight out. And then some of that goes actually into orbit and becomes debris and then falls back to the surface. So Sue would know about that. We learned about the RF spectrum, or the electromagnetic signals around the moon, the background signals from one of the payloads, which deployed antennas and could measure what the signals were that were coming from just the ambient noise around the moon, which has never been studied before. That was one of the most fascinating experiments. So quite a bit of learning. I would say every time we fly, as whether it's an agency or a company or an international partner, there's so much learning, there's so much experience gained. And so it's very important as we move forward in our moon program is to get flying and fly often with a regular cadence of missions so that we can just gain that knowledge. That's what happened in Apollo, right? In the Gemini and Mercury days and in Apollo, we flew and we flew and we flew. And we learned on every single mission. And that's what's happening now.
So when I see for myself that I'm part of something where you have a plan set forward and the plan goes as expected, you learn something. It's generally something pretty good. When things go off nominal and you have to sit and really think tank how to solve it, what's going on, the amount that you learn is tenfold more than if things just go nominally. So I'd like to thank Steve and team for taking one for the team, because the amount of information that we learned by landing sideways and seeing how everything bounced, the signals coming and going, were bouncing off the moon. This has been a big question mark. There are theories and ideas, but to actually see it in practice is a huge learning curve that we have needed to get over. We have plans to look at that for IM2, but the learning we did on IM1 was really important for future missions and making sure that we understand how the astronauts can work safely and be able to communicate with things bouncing off the moon. And that polarization thing, that was not expected going into the mission. So we've definitely learned things about the physics of how things behave on the moon that we did not expect, which I think is really exciting personally.
Yeah, we actually got the idea to how to resolve that and get the data from the vehicle from our ground station in Cornwall, England, at UK, called Goonhilly. And they spoke to us about that and said, you need reverse polarization is the way they talk. And we said that over and over again. And that's how we ended up, the decoder ring for how to get the images and the data off the vehicle.
Yeah, so UK accent, polarization.
That's right.
Wait, what are you saying? Yeah, so we are learning a little bit of the UK accent as well.
Fantastic. Well, I love what you said about how you learn things when the mission goes as planned, but you learn more when the mission doesn't go as planned. And obviously this is why we do simulations, but very rarely are the simulations that you practice really what ends up happening on the mission. And so the lessons learned from IM1 are not just beneficial to Intuitive Machines as a company, but like you're saying, Sue, to NASA as a whole. We're sending astronauts back to the moon with the Artemis program, and these missions are just lessons learned along the way of how we can best optimize those missions. And I would be interested to hear what other lessons learned we had during IM1 that we're implementing ahead of and during IM2.
Well, I'll tell you something. First point is, in response to your commentary, we stood on the shoulders of everyone who's gone before us, right? So we get the trophy for being the first commercial company to land on the moon. But all of the issues and concerns that happened in previous lunar missions, and more recently the lunar missions from the Barents Sheet lander out of Space IL, or for the iSpace mission, or for the Indian lander, or the Russian lander, all of those we saw, and we thought about those failures and implemented something on our vehicle to protect against that. Whether it's a different kind of propulsion system, whether it's different redundancy or multiple strings of redundancy, all of those kinds of things we thought about consciously as we saw those failures unfolding. So we really took benefit from those who tried ahead of us, right? But then we went through the mission and we had a series, we had what we call a hot wash after the mission, which is this review of how did it go? And we're self-critical. Not everything went great. So we generated a list of 65 items that we wanted to fix or make better between the missions. And so 10 of those went to IM2, and the other ones go to IM3, 4, and 5 subsequent, like enhancements. But what did we essentially have to fix? We would fly this mission again, like IM1. IM2 could be exactly the same with one fix the laser rangefinder and make sure that that would fire. And then we'd fly it again because it flies beautifully. But how can we do it with more precision, more accuracy, fix the laser rangefinders, fix orbit determination and the ranging of where you are in space at any given time? Those were the big things. And should we change the antenna configuration because we don't want to bounce off the surface anymore? But we didn't change it. We were going to land upright. That's what we did, make sure we're going to land upright. So those were just some comments for you on kind of the kinds of things that we looked at. But that formal process of going through and understanding what really went wrong and what needs to be fixed now, because we have a schedule and a budget too, and not everything can be added in right away. Some things take some time and some trade space and some understanding for the long term, because we're building a program for the long term. We're not building a one-off mission. And so how can we put block upgrades into Nova C? How can we move to heavier cargo on Nova D with the reliability we're looking at, we're wanting to achieve, right? That's kind of how we're managing the program.
We have similar ideas with the payloads. With the first round of payloads, they did a really good job at thinking through what kinds of payloads could actually help them with the mission. So unlike future missions, the early ones, the vendors actually chose the payloads that NASA put forward as options. One of them was NDL, the Navigation Doppler LiDAR. So even though their lasers weren't firing, we had a payload that was on board that still was able to collect the laser range finding data for us. So again, one of those teamwork where we could use our data to help them understand how the lander was landing. We had Lunar Node 1, which is an equivalent to a GPS type of communication system. And during the mission, when we needed to really get some help with navigating with the lander, I reached out to the LN1 lead, the PI, and said, hey, we need some help with some navigation. And he said, off the cuff, just no pause at all. We're a navigation payload. We're here to help you navigate, right? And so it's that back and forth, really working together in not just us helping them helping us, and then taking some of the lessons learned. Our Scouts payload was designed to look down and see the plume surface interaction from the engines churning up the dust on the surface. There was some redundancy we didn't have, so it didn't operate on the first mission. We have it on the next mission that's coming up that's actually in flight right now, the Firefly mission. So we've added some redundancies to that payload to ensure that they get the data that they need so that we can really understand that, to help us then use that data to ensure that we properly plan for how does the plume surface interaction tell us how we can better design our lunar landers and make sure that there's safety for the astronauts when they're landing as well. So it's helping for a future lander, and it's helping for future payload as well.
Yeah, one of the interesting things about Lunar Node 1, the payload that helped us with our trajectory going out to the moon, we were having trouble with the accuracy of our orbit determination. Where are you as you get further and further to the moon? Because the LN1 payload was active on the way out to the moon, they were actually sending their signals down through the deep space network and not using our ground network that we developed commercially. And so when our commercial network was having some trouble, the deep space network knew about us and was tracking us because of that LN1 payload. And therefore, we could actually get access to the deep space network to verify where we were in space when we needed it, because we hadn't scheduled it, and that doesn't work as real time as you'd like. It's fully booked, the deep space network. And so fitting it in was as a result of flying an LN1 payload and having that send a signal back to the Deep Space Network to help us determine where we were.
And talk about the personal side. The PI had a baby who was a week or two old at the time. So he was up at kind of crazy hours. So I was calling him at 3 and 4 in the morning, and he was like, yep, that's fine. I can jump in the car and go do what needs to be done to make sure that we can help with this. So yeah, all of our payload team, they were really, really great.
Wow.
So
I am loving this and loving reliving IM-1. It makes me more excited for IM-2. So let's dive into it. Let's talk about IM-2 and this new mission coming up, the lander. IM-1 was a Nova C lander. Is IM-2 the same? Is it the same spacecraft as before? And can you break it down for us?
Yes, IM-1, 2, 3, and 4 are the same lander. We're building the same core systems over and over and over again to make sure that we can have repeatability and reliability and robustness in our transportation leg or delivery system to the moon. So at their core, they're the same. But we're carrying a significantly more aggressive manifest of payloads this time on mission 2. And so it's a dynamic mission. There's deployable payloads all over the lander. So we deploy a drill, the PRIME1 drill suite. It's a Trident drill, so we'll talk about that, down to the surface of the moon and drill in 10-centimeter increments down a meter deep and measure the volatiles that are off-gassing out of the tailings pile and see if there's any trapped volatiles or water ice sublimating off of the tailings pile. Fascinating. But that's more important than finding the water ice, because really we're demonstrating the engineered systems that will help us prospect for materials and water ice in the future and in the Artemis campaign. So it's really learning about the techniques of how to do it. Another one is an invention that Intuitive Machines came up called the Micronova or Hopper. And it's fascinating because it's a mini lunar lander that flies off the side of the lander itself on a rail system. It's rocket propelled, and it hops 5 times along the surface, testing a communications system with Nokia Bell Labs, 4G LTE communications, the first cellular signals on the moon, or hop up to 5 times and then down into a permanently shadowed region where we carry 2 international payloads. One is a Pulley Space Hungarian payload that's a neutron spectrometer. Another one is a pyrometer from Germany, DLR. And we'll measure temperature and what the constituents are in the bottom of that permanently shadowed region. We'll take pictures down there, and then we'll hop back out. And so we'll be the first time in an area of the moon that's never seen sunlight and sense what's down in the bottom of that region. Another one, real quick, before you jump into, is the Lunar Outpost rover. We're flying and deploying a rover deployment mechanism where the rover is released down in a garage down to the surface, and the small rover drives out. And then we test this Nokia 4G LTE at shorter distance. So we can test both long distance communications on the surface and short distance communications. All of this precursor for sending deployed elements out while you're astronauts and LTVs and spacesuits, all those interconnections that have to communicate with each other. This is the precursor work for that. So very fascinating mission. International payloads. You have a Japanese rover that drops down to the surface from probably the engine deck area. And it sits about 2 meters off the surface and then just drops down onto the surface. 2-wheeled tail dragger that runs around a little bit. And then so there's 2 rovers, a drill, a hopper, all have to play nice together.
Well, I want to keep talking about the payloads, but this is a lot of payloads. So can you give us an idea of how big the Nova C lander is?
Yeah, the Nova C lander, fully fueled as we separate from the Falcon 9, Falcon 9 5500. We separate in a what we call a translunar injection orbit, which is about 385,000 kilometers by 185 kilometers, highly elliptical orbit. We're about 2,100 kilograms fully fueled. That's the weight or the mass of the lander. Empty weight is about 900 kilograms, so we take about 1,200 kilograms of liquid oxygen and liquid methane and helium to pressurize the system and then ignite and have the propellants drive us all the way out to the moon and break us into orbit. The size, it stands about 14 feet high, It's about 8 feet in diameter. So it's not a tiny lander if you look at it. It's pretty big. It's tall, cylindrical shaped or hexagonal cylinder with 6 landing gear on it, and an engine bell for liquid oxygen, liquid methane. The expansion nozzle sits about 2 feet. I'll mix my units 2 feet from the surface when we touch down.
Okay, so this is carrying every single payload that we've just discussed. And to get back to payloads, you mentioned PRIME1, and I know that's a NASA payload, correct?
It is. So the payload that we have is, it's going to collect science, but it's actually a Space Technology Mission Directorate, what we call STMD, because we love acronyms at NASA. So the goal of this is really to do some technology demonstrations, also in order to collect science. So PRIME1 is a combination of 2 different payloads, and PRIME1 stands for the Polar Resources Ice Mining Experiment 1. It's going to have the Trident drill. Again, like Steve mentioned, it's a meter. And for those of you who like football, that's about a yard. I think a lot of people understand yards, which is about 3 feet. So that's going to drill into the surface. And that's called the Regolith Ice Drill for Exploring New Terrain. These ones I have to read off because I don't remember these off the top of my head. And then M-SOLO is the Mass Spectrometer Observing Lunar Observations. So mass spectrometer, what's a mass spectrometer? What's a volatile? Let me get back to some kind of basics. So a mass spectrometer is an instrument that really is sniffing things that are easily turning into gas. So things like oxygen coming from the tanks, or methane, or water coming from below the surface, if there's any ammonia or methane ice that they bring up, whatever happens to come up from the surface, as well as the different gases that are potentially off-gassed from the lander, as well as from the hopper. Which reminds me, I just wanted to bring one little personal thing in, right? We talked about Odysseus, or Odie, being the first lander. The second lander is Athena, which we like to call Addie. So we have the female counterpart. And the thing that I love the most is the hopper is named after Grace Hopper. And Grace Hopper was this really groundbreaking technical woman decades ago. So they like to call her Gracie. So it brings a little bit of the personal into it. And she's such a little mini-me of the full lander that I'm really excited to see Gracie hopping around the surface.
If you say it fast, Grace Hopper. Sounds like grasshopper too, right? So the hopper is a hopper, and Gracie Hopper was a great name for it. And Athena, or Addie, well, Odysseus and Athena are in mythology. And so that was a natural progression where I guess they drilled in, Zeus had a headache, and they drilled into Zeus's head and released Athena. And so with the drill, the Trident drill and the PRIME1 payload, we thought it was important, the fact that she was born out of Zeus's head by drilling into his head. That was part of the story.
Oh, as a comms person, I'm loving all of the thought into this. This is fantastic.
So back to PRIME1, right? So the original science goal absolutely was to go to a more southerly location and be able to detect water. Because the mission is launching a little bit later, we're going to a slightly different area because that place is now kind of in shadow. Definitely in shadow. So it means that we're focusing more on the technology demonstration side of things, as opposed to potentially it's a low likelihood. It's not zero. Everybody looks at the models and says, we're not going to find water. But my personal experience, at least, has been that when I've been told you're definitely not going to find something, leave it to data to totally upturn a model on its edge, and have to be able to make sure that the models actually follow what the data is telling you. So I very much appreciate that this technology demonstration will also help us to better understand the moon and improve our models, because in the future, we really are going to need to use the resources on the moon for a future base that the astronauts are going to go to. So this is this resource mining that we keep talking about, where we are going to be able to understand the technology demonstration of how does a drill work on the moon? How does a mass spectrometer on the moon work in the actual environment of the South Pole? You can do all the tests you want on the Earth, but until you're in the real environment with the sun raining radiation down on you and the cold and the warmth fluctuating as the daytime goes by, you don't really have a truly good understanding of how good your technology works. So we will get that from the PRIME1 demonstration being a technology demonstration. And then one additional payload that we also have on is the LRA. So that stands for Laser Retroreflector Array. And it's another cute little payload. It fits in the palm of your hand. It looks like a little hemisphere. It has 8 quartz, what we call cube corner reflectors, which is a very fancy way of saying that if you take a laser and you shine it, that laser light will bounce directly opposite backwards to the source that sent the laser out. And the great thing about that is that it then allows us to very carefully pinpoint. We call them fiducial markers. That's a fancy way of saying that we are getting a really precise location on the surface of the moon of exactly where the lander is located, so that in the future, when we have orbiting spacecraft and we have landers coming in, having these fiducial markers at the South Pole will allow us to better navigate those landers to the surface of the moon. So it's exciting to have a couple of very different kinds of payloads for us, one passive and one very, very active with the PRIME team.
This is really an interesting mission from another aspect. When we talked, I mentioned in the beginning, the passion to build a lunar economy. CLPS has the drill package and the laser reflector array. The other payloads were aggregated into a single mission by Intuitive Machines. And so we went to NASA's Space Technology Mission Directorate, STMD, and we proposed with Nokia the LTE payload, and we were awarded that through STMD. It wasn't through CLPS that all that was put together. CLPS brought an anchor tenant, like the PRIME1 drill, but then we had to aggregate other payloads with a series of commercial, international, other NASA payloads, and the CLPS payload. And so this really is the beginning of how the commercial economy can start to take off. I mentioned a payload from Hungary, a payload from Japan, and a payload from Germany. There's also commercial payload to do testing of data warehousing on the moon for disaster recovery, like to store data centers there. So there's edge computing kind of ideas. And so there's also Columbia, who flew on our first mission, Columbia Sportswear, to test an insulating material. But there's a sunshade now that they're flying. So an insulator and a sunshade that comes out of the garment industry that is appropriate as an insulator on the surface. So non-traditional partnership. It's just a fascinating mission. And we're able to do that primarily because of the success of Mission 1. And so I see this building where more opportunities to fly a diverse set of payloads in partnership with NASA and others. You know, that's what's coming about here as the lunar economy begins to blossom.
And this is the beginning, right, of the Artemis program. The Artemis program is much bigger than just CLPS. We have all the other pieces that ultimately lead to the astronauts landing on the moon. We need to make a sustainable economy in the future, sustainable services on the lunar surface. These are the first pieces where we're sending robotic missions down to help us understand the lunar surface, to understand the environment of the moon, and to understand how to live and work there, how to communicate back and forth, how to use the things that are on the moon for what we call in situ resource utilization, which is a mouthful to say, can you go to the moon and be able to extract the water so that astronauts can have something to drink and oxygen to breathe and to create fuel so that you don't have to bring everything with you from the Earth to the moon to really create a future dwelling on the moon. So it's a really exciting thing that we are the starting point for understanding those things so that in the future, Gateway and Artemis and the other missions that we have as part of the full Artemis program can really learn and grow from this base that we're starting off with CLPS.
I wanted to go back to something that you mentioned, Steve. Some of the other commercial payloads that are flying, or partners, I guess, with Columbia, with Nokia, these are names that people are probably familiar with. Are these part of NASA's Tipping Point initiative? And can you tell us more about what that initiative is?
Well, the NASA's Tipping Point initiative is from the Space Technology Mission Directorate is to advance and do flight demonstrations or laboratory demonstrations on technologies that are promising for future space exploration. So there's a whole suite of ideas that they choose from in certain swim lanes of, studying the environment, studying space weather, studying survive the night technology, nuclear space, all kinds of different subjects that NASA is interested in learning about. Different capabilities that they're going to need. And the Tipping Point provides seed money to develop a payload. And some of them don't ever make it out of the laboratory. Other ones get to flight demonstration. And so for Intuitive Machines, what was important were the flight demonstrations. So Nokia and Intuitive Machines teamed up to develop a space-rated cellular communications radio and antenna system. And this is a time where the Space Technology Mission Director at STMD said, I want to see that fly. And so we're flying that. And that's amazing. And it's going to become a baseline for communicating on the moon if it proves out well. The drill was another idea. How do you drill into the surface of a planet? And the PRIME1 drill was a package STMD paid for. Other ones, like our hopper that we designed, was the idea of scavenging from an existing lander anything you could reuse on the surface. In situ resource utilization can also mean what's there, a lander, what parts of it could you reuse? And so we took the navigation pod, which has all the sensors to tell you where you are, and we said, what if we put a flight computer and a propulsion system on it and made it detachable? And out of it came Gracie Hopper or the Micronova or Hopper. And so that's where that came from for an extreme mobility payload. How do you move further and further away from the lander, your initial landing spot? And can you hop on the moon? Can you go to extreme places beyond where you touch down? And, the Hopper eventually has a capability of flying 25 kilometers away from the lander. So that's incredible. So all of these things were ideas that came out of stretching our minds, and the Tipping Point does that, to think of the systems you're going to need in the future to get to the moon in a sustainable way, to get to Mars, and resolve those technology barriers.
Yeah, so the Tipping Point is one of those strange in-between pieces on IM-2. We, NASA, have put a lot of effort into making sure that the PRIME1 Trident and M-Solo payload suite and the LRA are going to be flying to the moon. We have funded the development through this Tipping Point contract for the rover and the hopper, but the rover and the hopper are not managed by NASA. We are not the ones who are operating them either. So we operate Trident, we operate M-Solo. They operate, and it's there. We're just giving them the funding and say, go, you do everything. So it kind of then leads back to this concept where we talk about CLPS, but they are not CLPS missions. They are the vendor missions. We are one of the customers on their mission. It's actually the Intuitive Machines mission that's flying. But again, it comes back to this different way of doing business. And some of it is our payloads, some of it is their payloads, some of it is commercial payloads, international payloads, and some of it is NASA funding helping them to develop new technologies as well. It's a nice combination of many things.
It's a way of the future.
Yeah, going together.
Right.
Well, we've walked through Nova C, what it looks like, how big it is. We know now everybody that's flying on board talking about the payloads. So let's dive into the mission profile. Can you walk us through from launch to landing? What is this lander going to be doing?
Okay, so I talked about our launch from Kennedy Space Center, Launch Pad A on a Falcon, SpaceX Falcon 9 5500, which will take about 3,100 kilograms of payload into that orbit. That includes the lander. About 2,100 kilograms is on the lander, including all the payloads and all the fuel. But in addition to that, We have rideshare payloads that we've contracted with, and we put 3 payloads on the outside of what they call an ESPA ring, which is an embedded acronym like only NASA can do, the expended EELV, which is the expendable launch vehicles of the old days. So payload support assembly ring, ESPA ring.
You can remember that for the future, right?
Yeah, that's easy.
You told me I had to
rolls
spell
off the
out
tongue.
acronym, so I'm trying to remember. But we fly a JPL hyperspectral imager satellite called the Lunar Trailblazer. We contracted directly with Jet Propulsion Laboratory to fly that instrument and that satellite and deploy it from Translunar Injection Orbit, which is the 385,000 kilometers by 185 kilometers. And that'll separate after the lander separates from the booster itself. There's another payload that's going to an asteroid done by a company called AstroForge, and they're going to fly out towards an asteroid from that highly elliptical orbit that I talked about. And then a third payload separates, and that's a payload called EPIC, which will do a payload transfer demonstration in that for space exploration's future from that. And so there's things deploying all the way off when we're out into this highly elliptical orbit, and then we'll be on to the moon. It'll take about 7 days to transit from Earth to the moon. And Intuitive Machines lander, because it has a liquid oxygen, liquid methane propulsion system, has a highly energetic trajectory, which means we get out there very quickly, almost like the Apollo days. We don't actually take advantage of the gravity assist to wind ourselves out there slowly in 45 to 60 days like some of the other landers are out there. We go more direct. We'll then do 3 possibly trajectory control maneuvers to hone in and focus exactly our target point for lunar orbit insertion. That's key, because when we hit that target, we actually are in a good place to conduct that braking burn to take all that speed, the delta V, that we put in to get to the moon. We have to now reduce to 0 as we land on the moon. So you have to do this serious braking burn, slowing down and capturing in lunar orbit. And that's 100 kilometers by 100 kilometers in a circular orbit. And from there, we'll loiter till we process over our landing site. I'm using hand gestures on a podcast. That's not healthy. So we'll circularize the orbit and go round and round. We'll then lower our altitude, called deorbit insertion, till we get down to an altitude where we start our powered descent. And that burn is over 13 minutes long to brake and take that final delta V, delta velocity, out of the orbit and reduce it to 1 meter per second where we touch down. What's interesting is powered descent is done without any assist from the ground on the backside of the moon. So we initiate the burn before. We don't actually initiate the burn. We set it all up to burn, and this lander knows when to burn and ignites the engine when we can't talk to it, all by itself. And then we come down from 85 kilometers down to the surface. We take a measurement from our navigation cameras called terrain relative navigation, where we look at the craters going past, and we could determine our speed over the surface, and we could determine somewhat of our altitude based on the measurements that we're getting. And we'll come down, and as we descend, the last minute of flight is when we tip over and scan the landing site for hazards. And we can look for slopes that are less than 10 degrees and rocks that are smaller than a bowling ball. And we'll pick out a landing field and land in that spot based on what the hazard detection and avoidance system tells us. That's critical, because that's where we actually need the laser altimeters as we tip over, collect the landing site data, and then slowly throttle down to about 1 meter per second, and then touch down and fly right down into the moon. Because we don't want to hover, we don't want to bounce, we want to just fly. And then as soon as we touch down at 1 meter per second, the engine and the IMU, inertial measurement unit, sense that we're not descending anymore. We're not descending. And on a 3 count, it'll keep throttling down and shut the engine off. And then we're safely on the surface, and we wait for the signal, the heartbeat of the lander, to say, I'm alive. And that's when the cheering starts.
Well, how long does it take to get that signal?
Well, last time you were in the conference room behind the control room, and you could hear a pin drop as we waited for that carrier lock on the frequency, the S-band frequency. And it was some period of time, several minutes, where everybody was holding their breath. And then the release from the team when we said, we've got a signal. Yeah. We're on the surface. That was a tremendous feeling. A lot of cheering goes up at that moment. Then the hard work of running the mission once you're there begins, conducting the surface operations.
I think there might be hard work in getting there, too.
Yeah, maybe. Well, we're about out of time, but really quickly, I wanted to ask both of you, what's next after IM2, both for Intuitive Machines and for NASA?
So for NASA, we are launching for CLPS at a cadence of about 2 per year. And some of you may have seen the launch last week that Firefly had. So they are in orbit right now. They have a much longer transit period. So they are coming up on their landing March 2nd. So we're simultaneously working that mission with getting prepared for this mission as well. So that's been a lot of fun. And let's just throw some challenges. I think it's been great for all of us to learn, again, from each other, right? It's all about a teamwork of creating this lunar economy together. So those on the cadence of about 2 per year is what we're aiming for kind of for the rest of this decade, and then we'll see where CLPS goes beyond that. But it's been interesting that after these couple missions that are coming up, we have IM3 coming up next.
Yes, for Intuitive Machines, certainly we're going to keep that regular cadence of missions going with IM3 coming in about a year later. So that annual cadence is what we're aiming for. And on that mission we deploy the first data relay satellite around the moon that begins a constellation of satellites around the moon. So not only are we putting in the delivery system, the landers, and we're moving the landers through a regular cadence of missions to get to heavy cargo landers so that we can do a logistics supply. That's where we're headed. But we've added, building from Mission 1, that ground network of radio astronomy dishes around the world made us competitive, and we put in a bid to NASA to build out the Near Space Network services. And so we won those awards to put in the data relay network around the moon and the navigation scheme for how you're going to navigate, essentially the lunar GPS, and then all the ground stations commercially provided to communicate full spectrum from the surface to data relay to the Earth. And that's extensible from ex-geo, they call it, beyond geosynchronous orbit to the moon, and then from the moon out to 2 million kilometers. And so the first satellite goes up on Mission 3, and then the second 2 go on Mission 4, and the last 2 go on Mission 5. So that's what's in plan, and that's all part of laying in the infrastructure for a lunar economy.
Which is going to be really helpful, not just for future CLPS, but also for future Gateway and future Artemis missions as well.
Well, it sounds like it's going to be pretty busy, so a lot to look forward to.
Yes, very much.
But we are looking forward to IM2 right now. So thank you both so much. This has been a wealth of information that you've shared. And really, just thank you for coming and sharing your expertise with us today. We are cheering for Nova C, for Athena, I should say, and for the NASA payloads on board, that everything is smooth and successful. And I just can't wait to see what we learn this time. So thank you both.
Thank you very much. And one thing I'd add is Addie is currently in its shipping cradle, in its shipping container, waiting for the bridges in Louisiana to thaw out from our big snowstorm and ready to ship. So we're ready to go to the Cape, and it was supposed to be this morning, but the bridge is iced over, so we'll wait to get her safely tucked in at the Cape. We'll wait another day.
I can't wait to see the arrival.
Yep, should be a lot of fun. So excited to be able to work these missions, and really excited to be able to work with IM on IM2. It's going to be great.
Fascinating. Thank you both again.
Thank you.
Thank you.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0G, and I feel
The shuttle has cleared the sky.
became a theme for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.